Time to start our seminar. So today we have a very important speaker. You all seems to know, so we are having a lot of difficult times due to the recent pandemic conditions caused by COVID-19. So several scientific associations are being made and has been launched by our government. So one of them is the vaccine commercialization technology project. So today, this present speaker is heading the vaccine commercialization technologies projects and several scientific associations related to the infectious disease. So I would like to briefly introduce today's speakers, Professor Bang-Lin Song. So Professor Song graduated from the College of Pharmacy at Seoul National University and received PhD degrees from MIT University. So he has been served as a professor at the Department of Biotechnology, Yonsei University, and after retirement, he is now a special professor at Yonsei University College of Medicine. Is right, special professor. Okay, so today we're gonna talk about the chaperones and Chaperna, which means a chaperone personality, right? Yeah, and the pandemic vaccines. Please, Professor.
For the convenience, let me remove my facial mask. Okay, thank you. Thank you, Dr. Lee Kyung, for kind introduction on my behalf. And I'm really privileged to speak in the subject of pandemic vaccines, but the title seems to be a bit weird. Chaperona, you haven't been acquainted with this terminology. One thing I have to make excuse is that I was briefly misinformed on the date of my presentation, so therefore the date is misspelled a little bit. So so let me make a presentation on the pandemic vaccine, especially blending with the novel protein folding technologies that could be applied for the recombinant vaccine development. Since the COVID-19 is kind of matured, it's almost plateaued, although the outbreak is still persists. It may be appropriate for us to review for the past 2 years of what has happened globally. And one thing I should remember is that last year in England, there was a G7 summit meeting. Global leaders of 7 representing the countries gathered together in England and made a big declaration. There are several agendas, and one of the biggest agenda is, as shown here, is to develop a vaccine technology that could be deployed in a fast way, enough to control the infectious disease. So what they declared is that they would like to support the science in a mission to shorten the cycle for the development of safe and effective vaccines from 300 days to 100 days. What it means is that it took more than 300 days to deploy vaccines after the initial outbreak of COVID-19. The G7 global leaders declared the deployment, the time for the vaccine deployment will be shortened from 300 into 100 days. So speedy delivery is the mission to reduce the number of casualties. Traditionally, there are two important pillars for vaccine development. They should be safe and effective. Since the safety issue is very, very important for vaccine, especially because vaccine should be administered to healthy people, safety issue is very, very important. So in order to validate and prove the safety, the development time requires a long time, over 10 years. So usually over 10 years of development is required and a lot of expenditures. But under the backdrop of the pandemic outbreak, 10 years of development cannot be employed, can be implemented for the effective control of pandemic. Therefore, it should be shortened. Therefore, there are one important pillar added for vaccine development is safety, efficacy, and speed of deployment. With this agenda, 2 years ago, the United States declared a very important project on pandemic preparedness, so-called Apollo-style project. By then, the White House science advisor Eric Lander declared the US government will invest up to $65 billion for the next 10 years on pandemic preparedness, and probably about 40% of the expenditure will be spent on vaccine development. And we should focus on what he says is the vaccine infrastructure with a goal of beginning to manufacture vaccine doses meant to protect against any virus family within 100 days of pandemic threat, first imagine. So strongly emphasize on the speed of the delivery is the gist of the pandemic preparedness. And the same agenda has been well documented by CEPI declaration. CEPI is one of the global organization. It was established 5 years ago in Norway, in Oslo, for the preparation of the pandemic preparedness. And there are 3 different pillars of CEPI declared. Is that the fast delivery of the pandemic vaccines. For instance, the first corona vaccine was deployed after 300 days after the outbreak. But if we shorten the delivery time within 100 days, the number of casualties could be greatly decreased. But just in case of outbreak, just-in-time delivery is very important. Just to look at the various types of vaccine production platform. There are at least 3 different vaccine platforms, and among these, the mRNA vaccines and viral vector vaccine wins the race. And probably all of you were vaccinated by Pfizer or Moderna mRNA vaccines. I think perhaps some of you were vaccinated by viral vector vaccines about 2 years ago, developed by AstraZeneca. Both of the vaccine platforms, mRNA vector vaccine, has never been used before the COVID outbreak. Therefore, there is no safety issues cleared. Although the vaccine is effective, no safety record has been documented. However, in time of speed, no other platform can outwin the speed. Therefore, mRNA vector vaccine has won the race and has been used for the vaccination all over the world. So the important thing is the speedy delivery. In fact, more effective and more safe vaccines has been well documented by through the protein surveillance vaccines. However, actually protein vaccine it's developed by this SK Bioscience here and began to vaccinate about 2 months ago, 1 month ago. But 2 or 3 days ago, the Korean government declared that there is no more use of the protein vaccine because the protein vaccine is the original strain, is the Wuhan, the original strain. And since a number of the variant strains, Omicron and Delta variant appeared, and therefore the original Omicron, the Wuhan-based vaccine is no longer effective for the prevention. The reason being is that the protein vaccine requires long time of development, up to 2 years of development. So therefore, it lost the race. The currently developed SK Bio's protein vaccine is based upon two component system. One component is produced from microbial production. It's very fast because it used E. coli and microbial system, very fast and easily scaled up. And it provides a scaffold, but more important is the COVID-19 derived antigen, which is produced from animal cell culture. Animal cell culture takes long time and very, very difficult to scale up. Therefore, among these two components, the cell culture-based method, the component took long time, and therefore that's why this is the rate limiting step, provides a rate limiting step for the overall development of the protein-based vaccine. So let me come back to the 100 days mission. So in the COVID-19 case, Moderna and Pfizer developed mRNA vaccine and adenoviral vector vaccine developed by AstraZeneca ultimately wins the race because of the delivery speed. And the protein nanoparticle vaccine actually was not successfully able to provide the vaccine in a speed manner. But if this protein nanoparticle vaccine can be combined with the novel protein technology, that would enable the supply of the vaccine in a very fast manner, then it could be the protein-based vaccine may compete in the long run with mRNA or adenoviral vectors vaccines, maybe in the next pandemic, probably not in COVID-19, but other infectious disease of the pandemic potentials. So let me switch into a well familiar topic of the molecular chaperone. Are you heard about molecular chaperone in the undergrad biochemistry textbook in protein folding chapters? I think you are very familiar with the protein folding pathway. The nascent polypeptide chain out of the ribosome should undergo various folding pathway before adapting into native structure. One thing very important is that during the folding pathway, the folding intermediate is liable to misfolding into a non-biologically inactive form. As you know, there are a variety of the structures, alpha helical structure, beta conformation, and as well as a supersecondary structure. It should be all combined into a native structure. However, during this folding pathway, the folding intermediate is liable to misfolding into disordered aggregate. And if once this disordered aggregate formed, it is insoluble. It's very, very difficult to revert into this overall biological active conformation. So it's like a burnt down namdaemun. After namdaemun was burnt down, it took about 5 years to reconstruction, as shown here. So it's a difficult process to refold the inclusion body into a native conformation. And for example, the many biotech companies and pharmaceutical companies has tried the refolding pathway to regain the biological function of the native structure by refolding in vitro. However, this process is very difficult. Can be likened to the reconstruction of the namdaemun into the namdaemun you see today. So as the reconstruction in terms of architecture is difficult, the folding of protein into a native structure is very difficult process. If you can avoid this refolding process, and if you are able to produce your protein of interest into a native structure from the beginning, that would be very nicely combined with the production of a vaccine of antigens. Traditionally, the molecular chaperone has been defined as the one to assist the conformational folding and unfolding of large proteins of macromolecular protein complexes. For instance, when the client protein is made from the translation from ribosome, then if you leave this polypeptide unattended, it would go into a inactive conformation by misfolding. Therefore, the nascent protein should be protected from misfolding by the various types of molecular chaperone. For instance, DNA-K, DNA-J, or GROES type of chaperones all work together to help folding of the nascent protein into a native structure. So there are various types of molecular chaperones to assist folding, and the molecular chaperones are basically defined as the protein that assists the folding of the client protein. So molecular chaperones are proteins. That's the real definition. What is Chaperna? This word has been coined by the composite of the chaperone and plus RNA, trying to convey the idea that RNA, not a protein, can play as a chaperone. So RNA is a molecular chaperone. So actually, RNA has been well noted for the variety of functions. It functions as a gene in terms of in various types of RNA virus, including COVID-19 and influenza, and various types of RNA virus uses RNA as a gene. And also it can use a second messenger, mRNA. And also you know that RNA has an enzyme function. This ribosome function is also noted for RNA. As well as the RNA can play a function for gene regulation, so siRNA, microRNA, non-coding RNA, variety of RNAs can function as a gene regulation. This all types of various types of functions are noted for RNA, but however, the function in protein folding is relatively unknown. So we christened this function with a new terminology, Chaperna. If you can pronounce either Chaperna or as shape RNA. conveying the idea of the RNA determines the shape of the client protein. So if RNA provides chaperone function, how does it, the molecular mechanism would it be? So as shown here, the unfolded nascent protein undergoes a variety of the folding intermediate and into active, biologically active conformation. During this process, protein as a molecular chaperone binds and dissociates, and in order to facilitate, guide the protein folding into a productive pathway. If RNA emulate the similar function as the protein-based molecular chaperone, RNA would also interact with the folding intermediate in such a way to assist the folding pathway, guide the folding pathway into native conformation. Is it really possible that RNA would interact with protein in such a way to minimize misfolding? I think there are a variety of the RNA characters that could be utilized as a molecular chaperone. For instance, the folding intermediate, why? If it left unattended, it would lead to aggregation. It is because the hydrophobic residues are exposed into the aqueous environment. You know, water doesn't like hydrophobic residues, and that's why the definition of hydrophobic. So in this aqueous environment, hydrophobic residues exposed to water environment interact themselves and hide themselves inside of the molecular aggregate. So therefore, if this process is left unattended, basically all the protein folding intermediates lead into aggregate, insoluble aggregates with non-functional form. So in order to prevent it, the molecular chaperone steps in to interact with the hydrophobic residues, basically hydrophobic shielding effect provides this folding intermediate as a monomeric form and allows it exercise into folding intermediate. Therefore, the hydrophobic shielding is one of the most important character of the molecular chaperone. Does RNA is RNA able to provide hydrophobic shielding? There are a variety of indirect evidences that RNA molecules, especially base residues, pyrimidine and purine residues, is able to make hydrophobic interaction with amino acids in the polypeptides. That has been documented in the variety of hundreds of different type of RNA protein interactions that has been crystallized by and described by X-ray crystallography. Therefore, there is no wonder that RNA could provide hydrophobic shielding like protein-based chaperone. In addition, RNA provides another important function. The RNA protein interacting complex is negative, is highly negative charged because, as you know, RNA is the phosphate backbone is highly negative charged. Therefore, protein RNA complex is negatively charged. And negative charge repulsion between the folding intermediate actually desist. So desist the molecular interactions. Therefore, the charge repulsion operates between this among the folding intermediate, resulting in so-called social distancing effect. As you can be likened of social distancing, 사회적 거리두기 in COVID-19 situation. So 사회적 거리두기 is a kind of a government a measure imposed on society to keep the distance between each people to minimize the human-to-human transmission of viruses. So exactly the same mechanism operates here to keep it folding intermediate into monomer form enough to take the time for intramolecular folding pathway into native conformation. Therefore, RNA molecule mimics hydrophobic shielding and the masking effect of the protein-based molecular chaperone. And in addition, another important measure operates, so-called social distancing measure operates. It could be, if we combine hydrophobic masking and social distancing effect, probably Chaperna may perform much better than protein-based chaperone in terms of assisting protein folding. Yes.
So after supporting protein folding by RNA, so does it dissociate from the proteins and deleted or reused for the other protein as a?
That's an important question. Dr. Lee asked if after RNA bound to the client protein, does it dissociate? Yes, it should dissociate. If it stably maintains a complex, then it stops the folding pathway there. It should dissociate, to allow the folding intermediate to go to the next step. Therefore, not only the binding, but also dissociation is important. Therefore, there are various types of RNAs inside the cell. mRNA, big RNAs, non-coding RNAs, several kilobase long RNAs, as well as small transfer RNAs. We are focusing on transfer RNA. It's relatively small, and the tRNA protein interaction is known. It's a relatively weak interaction, is well known. Therefore, not only bind, but also well dissociate, enough to allow the folding of the client protein into native conformation. So let me go on to next. So if chaperone assists the protein folding in case of viral antigen, then this Chaperna technology could be used for the pandemic vaccines. For instance, if you look at the virus morphology of viruses are made up of the variety of proteins, self-assembled monomeric proteins. For instance, human papillomavirus, the capsid is made of 360 monomers. Norovirus is made of 180 monomers. Therefore, in order to make the virus-like particle, there are two requirements: folding of monomeric protein and then assembly of the monomeric proteins into supramolecular complex. There are two requirements required, and these two requirements is very, very difficult to achieve. For instance, native protein first should be made as a monomeric conformation, and then this monomeric conformation should assemble into a well-orchestrated multimeric complex. Therefore, there are two different types of death valley during this process: the misfolding of monomer and misassembly, defective assembly of monomeric antigens. Therefore, two different types, consecutive types of death valley should be overcome by a chaperone. And I think RNA could provide this chaperonic effect that will be shown in the experimental data later on. With COVID-19 vaccine, you have been vaccinated with mRNA vaccine. Although mRNA is it's a genetic material, the design of the antigen requires protein folding based design. Therefore, if you consider this COVID-19 antigen should be stabilized, the conformation should be stabilized enough to maintain a solubility and the immunological quality of conformation. Therefore, the antigen design of the COVID-19 is based upon the stabilizing mutations of the so-called prefusion conformation. And there are the introduction of stabilizing mutation actually provides a difficult extra step of difficulties in folding process, because in non-native type of introduction may skew the folding pathway enough to make misfolded monomers and the defective assembly. And therefore, the thermodynamic-based stabilization requires kinetic control of the folding and assembly pathway. And we can show that RNA provides this kinetic control enough to make the folding pathway into the native assembly process. So what type of RNA could provide the Chaperone function? This translation process, mRNA, ribosome-assisted protein translation into a polypeptide, is well known in the biochemistry textbook. In the later part of the biochemistry textbook, you are all familiar with this process. And in this process, there is important molecule, trans-RNA, clover leaf-shaped tRNA is very important. Trans-RNA has long been known as a kind of adapt molecule to translate the triplet codon into the amino acid sequence. There is an adapter molecule that trans-RNA anticodon base pairs with the codon in such a way that the specific amino acid residues are coupled together into a linear amino acid sequence. So it has long been known that trans-RNA has been an adapter molecule in translation. There is non-canonical function. For example, so you may call a moonlighting function of tRNA, which is not known very well, is the tRNA function of Chaperone. What I try to say is that after this next protein is made, it should be folded into a monomer, and the well-folded monomer further proceed into a quaternary structure. In virus case, it leads into a virus-like particle structures. What I try to say is that during this folding and assembly process, trans-RNA could be utilized as a chaperone for this folding process. So I want to show some of the example that Chaperna-based protein folding technology could be used for the generation of variety of pandemic vaccines. The misspelling. Virtually all viruses adopt very similar structure, so-called icosahedral structure. For instance, hepatitis P, human papillomavirus is made up of 360 monomers, norovirus 180, and yet they adapt into a very similar structure, icosahedral structure, with the 5-fold axis and 3-fold axis and 2-fold axis. It can be as as small as 60 different monomers can make this type of virus-like particle, or HPV case 360 monomers all operate together to make virus-like particles. Okay, what I try to say is that virus-like particle is based upon macromolecular assembly, and it probably requires a very potent type of chaperone to assist this molecular assembly. If you look at the text type of the virion assembly, it can be visualized by ordered fashion or random fashion. For instance, the monomeric form in the ordered fashion, monomeric virus first assembled in the trimer or pentamer, and then subsequently self-assembled into larger molecules. Or could it be random? However, either ordered or random process, one thing common is that inside the virus, there is a virus genome encapsulated into it. And you can ask how this viral genome, RNA or DNA, is encapsulated inside the capsid. Probably one process is that after capsid is near completion, then RNA genome, enters into the empty space and close the structure. That's one scenario. Another scenario is that not that passive manner, but RNA functions as a kind of an active role in the folding and assembly of the VLP assembly process. Then the RNA provides active role and can orchestrate the assembly of the virus, the genome of virus morphology. If I would like to prefer a kind of active role of RNA, if it functions as active, it probably functions as a chaperone for the folding and assembly process. So it should be verified by the experimental process. The approach we have taken is shown here. So if you want to assemble the viral antigen into this nice type of assembly, so before that, the viral antigen monomer should be folded in an immunologically active conformation. And during this folding process, we want to use RNA-based chaperone system, and the approach we take is that this target antigen is genetically fused with an RNA interaction domain. In this case, it's a transfer RNA interaction domain, and express this fusion protein in E. coli cell. Then, during this expression, the RNAs, in this case, the tRNA, that is present in E. coli cytoplasm, interact with this RNA and provide the chaperone function of the folding of this protein and the fused target protein as well. And after this soluble protein is produced, you can clip off this the junction and remove the RNA binding domain, resulting in a monomer that will self-assemble into a virus-like particle structure. We have a variety of experimental evidence that RID and tRNA interaction is very important in this process. If you mutate RID domain, defective in tRNA binding, then this folding process stops and all the proteins goes in the inclusion body. However, the RNA, as long as the RNA interaction persists, the transfer RNA assists folding and assembly of monomer antigen.
So
yes.
After remove the RNA binding domain, as you can see here, does it, I mean, does target protein are still maintains the native structures?
I believe so. But sometimes, if you remove RNA binding domain, sometimes the protein self-aggregate. So there is some unknown character of the target protein. So solubility is the most important part of this of the protein folding. However, solubility of the protein does not guarantee the native conformation. However, this process increases the possibility of adapting the target protein adapting into native structure. It's not a panacea. It's not the 100% solution, but it increases the possibility of the increasing solubility and subsequent assembly of the virus.
It should be confirmed that if you wanted to develop some kind of the vaccine, you should be confirmed that after collaborating the protein is what's going on the maintenance.
Sometimes the cleavage is not required for the self-assembly, sometimes, but for other cases it should be removed. Because if the RNA binding domain interferes, structure interfere of the assembly, it should be removed. But if it does not interfere, it could stay there. I can show you some of the examples that protein subunit vaccines could be made by the Chaperona system. There are several systems that we have suggested so far. Influenza vaccines, RSV and norovirus VLP particle. This shows the norovirus VLP particle, virus-like particle made of 180 monomers. If we cut in between, there is empty. So there is no infectious RNA genome. Therefore, if you make virus-like particle without genome, then it is very safe because it does not produce, it does not infect you. But however, the morphology-wise, it is just like the infectious virus, and therefore, after immunization, this morphology provoked very robust immune response, protective immune response. Fast delivery platform, the importance of fast delivery platform has been heightened during the COVID-19 situation. However, the importance of fast delivery is not the first case. As you know, the 2009 swine influenza novel influenza outbreak occurred, and about 140 countries were infected during 4 months of the initial period. And at that time, 14 years ago, the vaccine production speed took a long time and was not able to outspeed the virus, the spread. And by the time, the most common platform of the influenza vaccine production is embryonic egg-based system. It took about 6 months. After the swine influenza outbreak, there was a need for the faster delivery, and people worked very hard, a faster platform, and the second generation is cell culture-based one, but still required 4 months. Then, a biotech company called Vaccinate was established. They claim to provide the fast delivery of pandemic influenza vaccine based upon microbial system. And still, they do not have the solution for the requirement of Chaperone systems. And if you visit their homepage, they still claim that using the microbial system, they can produce the antigen within 3 months period. But initially, their initial objective is to reduce the production into 1 or 2 months, but without the effective folding and the assembly system, they were not able to achieve this over the past 10 years. So let me give you several examples of successful examples of pandemic vaccines. This is the RSV, respiratory syncytial virus. This virus infects infants and toddlers and with a high mortality. And in fact, the mortality rate is much higher than that of influenza. But still, there is no effective vaccine available globally. One of the leading institutions for the RSV vaccine development is Vaccine Research Center under NIAID in the United States. They have long experience on RSV vaccine. There's one prominent vaccine antigen is F protein. It's one of the surface proteins. And this F protein appears as a trimer. One thing very important of the RSV is to maintain the conformation of the RSF protein into so-called pre-fusion conformation, as opposed to the post-fusion conformation. That's a very pitch-dependent conformation switch there. Therefore, with respect to pH, the RSVF protein should be stabilized into a pre-fusion conformation in order to be vaccine effective. Therefore, the VRC, Vaccine Research Center, has long studied on how to stabilize, how to design the F protein into stabilized conformation. And this slide shows the paper published in 2013. They have produced more than 140 different constructs and was able to rescue only 4 stabilized mutants. Mainly because the rest of more than 100 different constructs failed to be produced because most of the proteins were produced as insoluble inclusion bodies. The technology they have is a thermodynamic stabilization process. However, they were not able to control the folding pathway enough to maintain its solubility and the folding status. So we tested among 100 different constructs. We tested several constructs which failed in the initial trial by the VRC, and was able to rescue those folding mutants into a native conformation by the Chaperona technology. Therefore, what we did is to use ferritin as a nanoparticle scaffold fused with RSVF protein in such a way that ferritin provides nanoparticle and the RSVF protein is displayed as an immunologically competent trimeric conformation. It was produced from E. coli, and the immunogenicity shows that this vaccine provides very robust neutralizing activity, and therefore there is a high chance to be successful as a recombinant vaccine. And actually, RSV nanoparticle vaccine has a long history, and Novavax is undergoing phase 3 study and will be ready for dispatch the world's first nanoparticle vaccines, and followed by United States Voyage Center, and Washington, Seattle has established two-component system, and this two-component system has been also utilized for the SK Bioscience two-component nanoparticle vaccines. And the process we have used is maintain the prefusion conformation in one component system, and unlike all these processes that utilized animal cell culture system, this Korean system uses microbial system that could be used for the fast production and very easy scale-up process. I want to show subunit vaccines, and you cannot ignore influenza vaccines. So this is the hemagglutinin trimer, and we made the head domain. This is immunologically competent domain into a trimeric formation, and one single nuclear phonetic chromatography of E. coli cell produce high quality antigen, and subject to site exclusion chromatography, we found that all these proteins, virtually all, over 90%, is present in the expected trimeric conformation. So after isolation of this trimeric, we immunized mouse, followed by virus challenge. We showed that all mouse survived, and with the potent neutralizing antibodies, and also the lung viral titer is below detection level after a challenge of the 1 week after challenge. So clearly, this recombinant protein provides sterile protection for the experimental mouse challenge model. And I think this is the first example of the microbial soluble production of the influenza pandemic vaccine antigen. I have some example of VLP vaccine and norovirus VLP. Norovirus, it causes acute gastroenteritis. There is a lack of cell culture method. Therefore, the vaccines based upon the virus culture is not available yet. The only method available is virus-like particle, and we show the stem structure followed by the bioimage processing shows that this virus-like particle exhibits 5-fold axis, 3-fold axis, and in between there is no virion RNA and non-infectious. 여러분들 속빈 강정이란 말 들어봤죠? 이게 속빈 강정인데요. 속빈 강정 하면은 굉장히 쓸모없는 걸 얘기하는데 우리 바이러스 인펙션에서는 속빈 강정 만드는 게 굉장히 중요합니다. 그래서 we successfully produced VLP vaccines in E. coli system, and previous method is based upon the animal cell culture. Animal cell culture developed by one of the famous pharmaceutical company, Takeda, Japanese-based Takeda established animal cell culture-based VLP. But E. coli-based VLP have an advantage in terms of speed and cost. We have some examples of nanoparticle vaccines. This is the encapsulin derived from the Mycobacterium tuberculosis. The encapsulin is made of 60 monomers, and single purification of the antigen and the examination on the EM shows that nice picture of the nanoparticle. Under the cryo-EM, the structure was solved with the resolution of 3.4 angstrom level, in conjunction with the Hostech group, and we were able to produce microbacterium-based nanoparticles, which could be utilized as a scaffold for vaccine antigens. Because time is short, let me continue on the flavivirus cases. Flavivirus comprises a variety of important pathogens: dengue virus, West Nile, Zika virus, and Japanese encephalovirus. And the antigen assembly is very similar, that the pentameric conformation is very important. We were able to assemble this pentamer based upon using the pentameric scaffold derived from toxins. Cholera toxin subunit is a pentameric scaffold, and if you use cholera CTB fusion with the dengue fever antigen, the dengue fever antigen is almost produced as a pentameric form. This is the native. This is SDS page. After boiling, it is monomer, and without boiling, virtually all protein assembled into pentamer, and therefore this pentameric fusion has been used for dengue vaccine prototype. Not only CTB functions as a pentameric scaffold, CTB functions as a mucosal adjuvant. Therefore, there is a built-in adjuvant system that increase the vaccine efficacy enough to be explored as an experimental dengue vaccine approach. So let me finish my talk. That I hope you could be persuaded by the microbial-based Chaperone system. It provides a delivery vehicle for low-cost and speedy production of vaccines. In terms of, for instance, the HPV vaccine is very, very expensive because it has been produced by animal cell culture and the higher eukaryotic cell culture. If you switch HPV vaccine into equivalent system, it could be provided as a very low-cost, affordable or premium vaccines for the countries in need, for South Asian countries and African countries. And also, it could be utilized for the speedy delivery of pandemic vaccines, as exemplified in influenza. But we have not provided the experimental evidence of corona yet. It's ongoing effort there. And emerging neglect disease vaccines, including Zika, dengue virus, Nipah virus, is within our range of vaccines. And unmanaged vaccine, of course, still RSV vaccine is not available so far. If we succeed in the commercial process, then probably RSV vaccine can also be available as a low-cost vaccines as well. Probably time is up. I should stop here, and thank you for your attention.
Okay, thank you for great presentations, Professor Chang. So time is not enough, so we would like to take one or two questions. Please.
Yes.
Thank you for your wonderful talk. So I was wondering, in addition to tRNA, is there any other RNA which can act as a Chaperna?
Yes, that's a great question. The reason why we focus on transfer RNA as Chaperna, prototype Chaperna, is that there are a variety of tRNAs present, about more than 60 different types of isotype of tRNAs, and tRNA is well known that it can interact with many proteins by weak interaction. It's based upon the Professor Lee's earlier question, the Chaperona function. If we should provide Chaperona function, it not only interacts with the a client protein, it should also be able to dissociate. There is a weak interaction is important. And the variety of tRNA function is available there. And also, the tRNA is very small. The functionally and structurally, it adopted the clover-leaf structure. It's a very elegant three-dimensional structure and is able to provide a variety of interactions. And it is also possible that other non-coding RNA provide chaperone function, but that's beyond our experimental approach, ability of our experimental approach. It is possible that human produce a lot of the non-protein. It is genetic information. The human genome is made of the information of variety of non-coding RNAs, and there are many studies on the function of non-coding RNA. And I believe that one of the non-coding RNA function is Chaperna, but probably requires a lot of further studies. Yes.
When you select a specific tRNA, you usually screen the tRNA from several isotype tRNAs, or the different tRNA shows the similar activity?
Maybe that's the next round of experimentation and exploration. But the tRNA we are using so far is lysine tRNA. It is derived from the RNA interaction domain is derived from the human lysine tRNA synthetase. It's about 800 amino acid long synthetase. But although it was derived from human, it can also interact with E. coli tRNAs if the gene is expressed in E. coli system. As mentioned before, the tRNA can interact with variable proteins through weak interactions. So far, the tRNA we are using is the lysyl tRNA, but we have an evidence that other tRNA provide similar function as well.
I would like take one question in Korean student speak.
Yes.
교수님께서 그 박테리얼 시스템에서 정제하신 거 관련해서 제가 여쭤보고 싶은데요.
잘 안 들리는데 크게.
박테리얼 시스템에서 그 타겟 프로테인을 정제하신 거에 관해서 좀 질문드리고 싶은데요. 가끔씩 간간이 그 타겟 프로테인을 박테리얼 시스템에서 정제하면은 그 DNA K가 같이 딸려 나오는 경우가 많아요. 그거는 어떻게 리무브할 수 있는?
좋은 질문 해주셨어요. 이 드나K가 이게 well-known molecular chaperone. 그렇죠. 그러니까 우리가 원하는 단백질을 오버엑스프레션 하면은 그러면 드나K와 같은 molecular chaperone들이 이런 폴딩을 도와주려고 이렇게 붙어 있는 경우가 많아요. 그런데 내추럴 시스템보다는 지금 우리가 오버엑스프레션 시스템에서는 이 단백질 원자가 많잖아요. 그러니까 많기 때문에 드나K가 상대적으로 좀 적어요. 그렇죠? 적기 때문에 충분히 이것을 폴딩을 도와주는 이런 서케미트리 와이즈 이것이 충분하지가 못한 것 같아요. 그래서 많은 경우에서는 이게 붙었다 떨어졌다 붙었다 떨어졌다 하면서 폴딩을 도와줘야 되는데 많은 경우에서 붙은 상태로 같이 침전으로 가는 경우가 많아요. 아시다시피 우리가 프로틴 폴딩 디지즈 중에 프로테오패식 디지즈 중에 소위 그 인큐전밥이 그 플라크 떨어지는 단백질 그 플라크를 자사포별 휴먼에서 그게 드나K와 같은 이런 샤프론하고 애그리게이션의 상태로 있는 경우가 많아요. 어쩌면은 폴딩을 도와주려고 하다가 무너지는 이 폴딩이 무너지면 뭐 지붕이 무너지고 건물이 무너진다고 합시다. 이 폴딩을 이것을 막아주려면은 드나K와 같은 샤프론의 바인딩이 돼서 이게 막아줘야 되는데 힘이 없으니까 같이 무너집니다. 그래서 지금까지의 그 프로틴 폴딩 디지즈에도 아마 제 생각에는 이 RNA 이쪽에 샤프론 이펙트를 더 연구를 해야 된다고 나는 생각해요. 지금까지 폴딩 디지즈에서 무슨 ALS라든지 그 파킨슨 디지즈 대부분 프로틴 중심으로 해서 연구를 하고 있는데 아마도 우리가 더 연구를 하면은 그런 폴딩 디지즈를 일으켜줄 수 있는 단백질이 미스폴딩 되는 과정에서 어쩌면 미스폴딩을 막아주는 그 RNA 몰레큘이 efficient하다든지 이와 같은 환경에서 일어나는 것이 아닐까라는 생각을 해볼 수도 있을 것 같거든요. 10년, 20년의 주제라고 생각합니다.
So why don't you ask us some COVID-19 vaccine and government policy? Because Professor Song is very specialized in this field. Whatever those are, you can ask us Korean language. Okay. Is there any question?
If I answer each question, I would like to answer this.
Yeah.
The COVID-19 vaccine is kind of dominated by mRNA vaccine technology. And the company that developed mRNA vaccines.
Just one question, sir. Just in case. Why don't we develop any novel COVID-19 vaccine? Even we have a lot of environmental, scientific environmental research areas we have. So why don't?
Well, it's not do or don't. It's a question of whether you can.
Just one question is there any?
Well, it really it's a matter of our technology developed. The vaccine technology so far is not mature enough to respond to COVID-19 situation. And I'm partly responsible for it as a vaccinologist. But probably with the COVID-19 situation, the vaccinologists and immunologists like you should be more alarmed for the incoming the threat. And we have to collaborate with each other to develop vaccines to be available to the people and to countries as well.
So thank you so much. So any questions? So it's time to close this seminar. Thank you.